Hello, my name is Philip Wing, and I am a member of Team14, colloquially known as Auto Games, for the Spring 2022 edition of the Integrated System Design2 class at Clemson University. My other teammates are Anthony Dodd, Brian Huber, Landon Hill, and Brandon Edmonds. Our project was to build an automated chessboard. Next, for objective motivation. We chose to build an automated chessboard over the course of this semester with a budget of $400. We wanted to build an automated chessboard because chess is a classic, fun, and challenging game that appeals to an international audience. We also thought our collective skill sets and experience would complement the tasks associated with conquering such a project. For project goals and deliverables. In order to construct an automated chessboard, a comprehensive chess AI was created through the use of a neural net that would follow all the rules of chess and compete at an acceptable skill level. The chess AI was then incorporated into a self-made chess app that allows a player to play against it. The player's input is relayed to a Raspberry Pi, which validates the requested move and monitors game piece positions on the board through the implementation of Hall-effect sensor grid underneath the playing surface. The Raspberry Pi also controls a robotic arm that moves pieces according to the input received by the chess app. After a piece is moved, the sensor grid would relay its information to the Raspberry Pi, which would then be able to validate the piece's arrival at the expected square. Now I'll let Anthony talk about how we approached designing our project solution.
Thanks, Philip. The automated chessboard takes inputs from either an app or a chess AI that then relays this information to a Raspberry Pi that monitors the state of the chessboard. After receiving the input, the Raspberry Pi outputs a signal to a motor driver that controls the motors of a robotic arm in order to move the chess pieces. Along the bottom of the chessboard is a grid of Hall-effect sensors that relays piece positions to the Raspberry Pi. This sensor grid creates a closed-loop control system for the Raspberry Pi, where the received input and given output can be verified. If the input and output conditions do not match, the Raspberry Pi can appropriately respond to the situation. The Hall-effect sensor grid is made up of a total of 96 Hall-effect sensors, with 64 of them monitoring the 64 squares on the 8x8 chessboard. The other 32 Hall-effect sensors monitor the capture zones on each side of the board. The sensor grid is divided into 6 sensor rails of 16 Hall-effect sensors each. Each sensor rail has its own multiplexer with 16 input pins that are connected to the output pin of the Hall-effect sensors. Each multiplexer has 4 output pins with color-coded wires that represent the select inputs. The wires are coded in a rainbow pattern of orange, yellow, green, and violet for ease of rewiring. Every 2 multiplexers' select inputs are wired to a shift register, with a total of 3 shift registers monitoring the sensor grid. Each multiplexer also has a signal output that is directly wired to the Raspberry Pi. The next major system is the chess engine, which Brandon will discuss.
Thanks, Anthony. The chess engine works using 3 main functions, the first of which is the valid chess move function. The valid chess move function looks at the internal game state and takes its input as the starting location and ending location of a piece, then determines if the move is legal or not. Given a legal move, the move chess piece function can then be used to update the internal board state by moving the piece. It updates things such as which player has the turn, whether or not kings are in check, and whether or not the game has ended, for example, checkmate or stalemate. The internal chess state is then used by the AI, which uses a long short-term memory neural network to predict potentially good future moves. A heuristic evaluation function is used alongside the neural network to determine the viability of moves by looking forward into the game a given number of turns to determine how good the move is. Next, I'll let Landon talk about the Android application GUI.
Thanks, Brandon. In order to play chess, our team created an Android app. This works by sending HTTP requests to a web server which is hosted by the Raspberry Pi. This allows us to validate the player's move and to track the gameboard state. The player can either play against a human or an AI engine that our team develops. The player is alerted on the GUI whenever a piece is selected, when the user requests a hint, or when the player is in check, or when the game is over. I will now hand it over to Brian to talk about the motor controls.
Thanks, Landon. For controlling the SCARA Arm, two NEMA 17 stepper motors and TMC 2208 motor drivers were used to provide easy control over direction, speed, and precision of the motors. Microstepping was also used to increase the standard steps per revolution from 200 to 3,200, reducing the amount of jitter and increasing the precision in controlling the SCARA Arm. Next, I'd like to talk about the robotic arm we used for this project. Inspired by a reference project on hackaday.io, we decided to implement a SCARA arm to move the chess pieces around the board. This approach involves an electromagnet attached to the end of the arm and a magnet installed in the base of each chess piece. Initial research showed we wouldn't be able to simply buy a robot that suited our application. So after some searching, we found an open source SCARA robot with 3D printable pieces that was programmed in Python. Having 3D modeling, 3D printing, and Python experience, we chose the JJ Robots PyBot as the foundation for our SCARA arm. The main modifications that we had to make to the reference design were the removal of the Z-axis and related hardware, widening of the base to accommodate inverting and seating the two NEMA 17 stepper motors, lengthening both the upper and lower arms to reach the farthest corners of the board, and changing the end of the lower arm to hold an electromagnet instead of a gripper. Unfortunately, we discovered the files for 3D printing the different pieces were trickier to modify than we had anticipated, and we ended up rebuilding the pieces in SolidWorks instead. Lengthening the arm requires some geometry to calculate the farthest distances, and also calculating the new belt circumference. Throughout this process, a SolidWorks assembly was maintained and used to check part fitment and functionality. Now, Brandon will talk about our performance analysis.
Chess AI performs better than expected, being able to make predictions in only 5 seconds on the Raspberry Pi, while also being able to beat chess players at 1000 ELO, which represent beginner to intermediate level chess players. All chess rules behave as anticipated, being fully implemented, allowing chess to be played, and the GUI takes user input and communicates the data with the Raspberry Pi successfully, such that the Raspberry Pi can move the electronic arm and control the motors as anticipated, being able to move the electronic arm 30 millimeters such that pieces can be moved and all Hall effect sensors correctly sense all magnets within the center of a square. Some of the strengths of our project include that the AI move prediction function performs well using the LSTM neural network and heuristic evaluation function combination, which is different from most chess AIs which use reinforcement learning. On top of that, we had a closed-loop system due to having the Hall effect sensors, and we were also able to control both the GUI and motor simultaneously due to the use of threading. Now Landon will talk about some of the weaknesses of the project.
For the weaknesses of our project, the SCARA arm that we built wasn't as accurate or precise than when we compared it with the simulation code, mainly because mapping the simulated coordinates to the physical board took a lot of trial and error and hasn't been perfected completely yet. Another weakness is the wires that we connected from the Hall effect sensor grid to the multiplexers, where we've had issues where occasionally a wire may come loose, and that can cause errors in our closed-loop system detection. Another weakness is the missing functionality in the GUI, such as a start over button or an option to select which color you'd like to play as. Currently, the user has to close and reopen the app in order to restart the game. Okay, so this is the motor arm simulation. This is the GUI we created. So for example, if you move the white chess piece up 2 squares, the simulation will move down to grab the white piece, and then it'll wait, and then it'll move up. And as you can see, the arm is also attempting to move down and grab the white piece. And then after that, it resets to its original position. For reconsidering our project design, we believe that using an XY plotter for controlling the pieces would greatly reduce the amount of complexity in building an entire arm from scratch, such as the amount of time that was needed to redesign and 3D print individual parts, or the complexity of modifying external Python libraries to suit our project requirements. Another consideration was using the HE10 connectors instead of individual wires that caused issues from loose connections. This will greatly simplifying the wiring nest that we created and help for future debugging. Other features we would like to include is an array of LEDs under each chess square for visual feedback to the user, such as which piece they moved or whether they're in check or not. The same could be applied for audio feedback as well. In the GUI, it would also be helpful to have a start over button or have the ability to swap between playing as black or white.